This is the awe-inspiring tale of how a group of brilliant scientists dedicated their lives to uncovering the fundamental building block of the universe. Through years of research and tireless experimentation, they were finally able to detect the elusive field, a particle so fundamental that it gives mass to all other particles in the universe. Without this particle, there won't even be galaxies, stars or our universe. One might think that this is the kind of scientific discovery that would end the age-old debate of whether God created our world or not. The scientists were successful in identifying this particle field and even won a Nobel Prize in 2013 for this. Do you know what that elusive particle now commonly called? The God's particle. In the world of particle physics, there are few things more thrilling and dramatic than the search for the elusive Higgs boson. Proposed by brilliant physicists Peter Higgs and François Englert in the 1960s, this subatomic particle was a crucial piece of the standard atomic model. But for decades, it remained nothing more than a theoretical concept. That all changed in 2012, when scientists at the Large Hadron Collider in Switzerland finally discovered evidence of the Higgs boson. A moment that shook the very foundations of physics and set the scientific community ablaze with excitement. But what is the Higgs boson, really? In the high-stakes world of particle physics, there exists a field that holds the key to the very fabric of our universe. This field, known as the Higgs field, is responsible for giving mass to particles, and without it, the particles would be weightless and the universe as we know it would cease to exist. Imagine a world where everything around you is weightless, where objects float aimlessly and structures crumble into oblivion. This is the fate that awaits us if the Higgs field did not exist. After decades of intense research and experimentation have led us to the discovery of the elusive Higgs boson, the particle that gives mass to other particles. The very existence of this particle confirms the existence of the Higgs field and unlocks the secrets of our universe. Despite its evanescent nature, the Higgs boson is a critical component of the Standard Model. And with its discovery, scientists have confirmed what they've long suspected, that this elusive particle is the key to understanding the fundamental nature of our universe. Long ago, the ancient Greeks were pondering the nature of matter. One philosopher, Democritus, proposed that all matter was composed of tiny, indivisible particles he called atoms. But for centuries, Democritus' ideas were largely ignored. It wasn't until the 1800s that a British chemist named John Dalton revived the idea of the atom. Dalton believed that atoms were the basic building blocks of matter, and that they could combine in simple, whole number ratios to form compounds. But Dalton's atomic theory was incomplete. It wasn't until J.J. Thomson's discovery of the electron in 1897 that scientists began to understand that atoms were made up of smaller particles. Thomson's discovery of the electron was a game-changer, as it showed that atoms could be divided into smaller, subatomic particles. This led to Ernest Rutherford's experiments with alpha particles and gold foil, which showed that the atom had a small, dense nucleus at its center, containing positively charged particles called protons. The discovery of the neutron by James Chadwick completed the picture, showing that the nucleus also contained neutral particles. In the quest to unravel the mysteries of the atom, scientists were left with a puzzling question: what made up the nucleus of an atom? The proton had been discovered by Rutherford, but what about the elusive neutron? Decades passed with no answers until the 1960s, when Murray Gell-Mann and George Dwight proposed a stunning theory that would shake the foundations of subatomic physics. They suggested that protons and neutrons were made up of even smaller particles called quarks. These quarks, with their different flavors and charges, posed an entirely new set of questions. How could these tiny particles come together to form protons and neutrons? The answer was a force unlike any other, one of the four fundamental forces of nature, the strong nuclear force. This powerful force was responsible for binding quarks together and holding the nucleus of an atom intact. And it is carried by particles called gluons. These tiny messengers interact with the quarks in protons and neutrons, creating a forceful glue that holds the particles together in a tight, At its core, the Standard Model divides the building blocks of matter into two categories, quarks and leptons. Quarks, the fundamental particles that make up protons and neutrons, are further divided into three generations, each with two particles. The first generation includes the up and down quarks, as well as the electron and its corresponding neutrino. The second and third generations include heavier versions of these particles, with similar properties but greater mass. The Standard Model also includes the fundamental forces of nature, which are carried by particles known as bosons. There are four known fundamental forces: the electromagnetic force, the weak force, the strong force, and gravity, which is not part of the Standard Model. Each of these forces is carried by its own unique particle, and together they weave the fabric of our universe. But physicists were struggling to understand the nature of the weak force, which was a perplexing mystery. Then, a brilliant idea emerged from the minds of Sheldon Glashow, Abdus Salam, and Steven Weinberg: what if the weak force and the electromagnetic force were actually the same thing? This idea became known as the electroweak theory, and it was a revolutionary concept that changed the way we understand the universe. As per the electroweak theory, there is a single force that governs both the weak force and the electromagnetic force, called the electroweak force. At low energies, the electroweak force behaves just like the familiar electromagnetic force, which we experience every day. But at high energies, the electroweak force behaves like the weak force, which is responsible for processes like radioactive decay. In the 1960s, a group of brilliant physicists proposed a daring theory that shook the foundations of science. They postulated the existence of a mysterious field that filled the entire universe, and interacted with particles to give them mass. This field was known as the Higgs field, and it was the key to unlocking one of the greatest mysteries of our time. According to the theory of the Higgs field, particles acquire mass by interacting with the field, which permeates all of space. When particles move through the Higgs field, they experience a resistance, similar to the way a swimmer experiences resistance when swimming through water. This resistance slows the particles down, and they appear to have mass. In particular, particles that interact more strongly with the Higgs field will have more mass. This explains why particles like the top quark, which interact strongly with the Higgs field, are much more massive than particles like the electron, which interact more weakly with the field. According to the electroweak theory, the Higgs field interacts with the weak force carrier particles, called W and Z bosons, as they pass through it. This interaction slows down the W and Z bosons, making the weak force very short range. Without the Higgs field, the W and Z bosons would be massless, and the weak force would be long range and as strong as electromagnetism. For decades, the Higgs boson remained a theoretical concept, shrouded in mystery and speculation. But in a bold and audacious move, scientists built the world's largest particle accelerator, the Large Hadron Collider, LHC, to test this theory. The LHC was capable of colliding protons at mind-boggling energies, recreating the conditions that existed shortly after the Big Bang. In 2012, two teams of scientists working at the LHC, one led by Peter Higgs himself, announced that they had discovered a particle consistent with the Higgs boson. As if the discovery of the Higgs boson wasn't thrilling enough, the story of its nickname adds another layer of drama. Nobel Physics laureate Leon Lederman, a leading particle physicist and former director of Fermilab, wanted to call it the goddamned particle because of how elusive it was. But when he used that phrase in an interview with a newspaper reporter, they couldn't print it. Instead, they went with God particle, which made sense as it imparts mass to other particles. Despite Peter Higgs' preference for the Higgs boson name, the nickname stuck and even became the title of Lederman's subsequent book. Now commonly referred to as the God particle, it symbolizes the fact that no matter how hard and how deep you dive into something in science, you may ultimately have to give credit to God. It's a name that carries both controversy and a sense of awe, befitting of the mysterious particle that has captured the imagination of scientists and the public alike. Thanks for watching. Please do like, share and subscribe.